Hi, and welcome to slope fields. A slope field is a representation of a differential equation on an xy plane. So basically they're going to give you a differential equation, that's just a derivative equation, solve for dy over dx, and they're going to give you a grid of some sort with some x and y coordinates, and then you are going to create little line segments that represent the slope of the tangent line at each of these points. So to create a slope field, what you're going to do is look at your differential equation in the grid provided. You're going to find the x and y coordinate of each of the points and only the points that they ask us to find a slope field for. Excuse me. And we're going to plug that into the differential equation. And please remember that dy over dx is just the slope of the tangent line. Once you plug that into the equation, that answer is your first derivative. That's the slope that you're going to generate at that point. You're going to mark this on your grid by making little tiny line segments with the slope. You're going to do this for every point on your grid. So instead of having an equation and you're finding the slope of a point on that equation, you're given a derivative and you're finding what the slope would look like at each and every point. Now, each and every point on that grid may not be where your particular equation turns out to be, but you'll see what I'm talking about after we do our first little example. So this is what it's going to look like. They're going to ask us to create a slope field. Notice you have your differential equation. Differential equation, don't get all caught up. It just means it's a derivative and it's an equation. So dy over dx equals x. So this is a very simple differential equation. Now notice they give us a grid here, okay, of 9 points. Now, depending upon the problem, they're going to give you different points, so just be aware of that, looking at each of those points. Looks like creating straight lines did not improve since the last time we joined each other. All right, so when I'm looking at these points, I have where I've got 0, 0, 1, 0, negative 1, 0. I have all of these points, and we're going to have these just go by ones. But I didn't want to put the little notches on there because when we draw our slope field, you're going to see what we're talking about here. So we've got the point 0, 0, the point 1, 0, and the point negative 1, 0. Then we've got the point 0, 1, 1, 1, negative 1, 1, and then the point 0, negative 1, 1, negative 1, and then negative 1, negative 1. Okay, so these are just the coordinates of each of these points on this grid. Now what we're going to do is we're going to plug this point, so the point x equals 0, y equals 0, and we're going to plug it into our differential equation. Let me use a different color here. We're going to plug it in right here. Well, notice we don't have a y coordinate to plug in, so our derivative is going to equal the x coordinate. So this becomes really a nice little experience for us. So this is the derivative at each one of these little points, and then we're going to create a little line segment representing this slope. Now they're not going to get out a little protractor and make sure, well, is that really a slope of 1? Is that really a slope of 2? No, they're going to look at, are your slopes positive where they're supposed to be positive? Are they 0 where they're supposed to be 0? Are they negative? If one slope is steeper than the other, your little line segment should represent that. But they are literally going to be looking at your slope field and getting that general idea. So when I put these on here, everywhere my x coordinate is 0, I have a 0 slope, so that's just going to be a nice little horizontal line. Everywhere x is positive, I've got that slope. I'm going to try to make those slopes the same, okay, parallel all the way through. And then these guys are negative 1. So looking at this little slope field, we don't know what the exact equation is going to look like, or rather, we do know what the exact equation is going to look like, but we're creating a little slope of a tangent line at every point in this xy plane, every point that they ask us to find. Now, if we were to take this equation and solve it, Okay, we would separate and integrate. Okay, so we separate our variables, we integrate. Well, the integral of dy is just y. The integral of x would be x squared over 2 plus c. So you can see that this differential equation represents this actual general equation. Notice, because we have the plus c, that's what causes us to not know the exact equation. But we do know that it's a parabola, and if you notice, look at this, you see that nice little parabola. Where your parabola is depends on what your c value is. So we could kind of get an idea of what these actual equations would look like. General, because of the plus c, if we had a point on this exact equation, we would be able to narrow down which of the parabolas it did represent. So in an AP type question, a lot of times they'll ask you to create the slope field, which is just our little red notches here. And when they're looking at these, they're really not even going to be looking at our xy, dy, dx chart. They're going to be literally looking at these little segments. It's not really difficult, so they're really probably only going to give us 1 or 2 points. Then they're going to ask us to find the general solution, and that's what we've done right here. And that is usually going to be 5 to 6 points as well. Okay, so let's look at another differential equation. Okay, this time it's dy over dx is equal to y equals 2. Notice we have the same exact points, so I've just created my little xy points, and it's the same exact 9 points that we've been working with. Well, this time, notice I just have a y. I don't have any x's. So when I plug this into my differential equation, I'm going to have my y coordinate divided by 2. So that's going to be 1/2, that's going to be 0, negative 1/2, positive 1/2, 0, negative 1/2, 1/2, 0, and negative 1/2. Okay, so there were just y's in our differential equation. So basically I didn't even really look at the x coordinate at all. So when I'm graphing these, I have where my y value is at 1, I'm at positive 1/2. So I'm going to make these. Now if I had a slope of positive 1, I would make sure that it looked steeper than this 1/2. Where y is 0, my slopes are 0 or horizontal. And then I have my negative 1/2. So I try to make these negative and as steep as the positive version. All right. Now, looking at my differential equation, awfully pretty. They want us to find the general solution, so we are going to separate and integrate. Well, this time I'm going to have to divide by my y, so I have dy over y equals 1/2 dx. And then don't forget to let them know that you are integrating by putting the integral symbol there. Without it, they don't really know what we're doing. And then when I integrate, I'm going to have the natural log of the absolute value of y equals 1/2 x plus c. And then I can get rid of my natural log by e-ing both sides, so to speak. And remember, it's important for you to remember this plus, that is a property of exponents. When you add exponents, you are actually multiplying. And then this guy right here can be renamed as our c. So that's going to be c times e to the 1/2 x power. Okay. And so when you're looking at that, you can see those little general equations. Looks like a little exponential. You've got the little exponential equations that could be going down. Okay. Now when they ask you to do a create a slope field, you do not have to fill in these little equations here. So these little dotted blue things or the green things on this slide before, you are not going to be doing that unless they specifically ask you to draw in the general equation. Okay? So generally in a AP situation, this is going to be 1 or 2 points. This is going to be 5 to 6 points, depending upon how difficult the differential equation is. And then usually they'll ask you to do 1 or 2 additional things, something else like generate the particular equation or to analyze the situation at points. So let's look at yet one more differential equation. Now when I'm looking at this one's a little more difficult. Notice I have the same 9 points, so this T-chart here looks exactly the same. But this time I have an X and a Y. So I'm going to have some unusual situations here. So I'm going to have X divided by Y, so that's 1. Ooh, 1 divided by 0, that is undefined. Well, when you're undefined, you're going to have a little vertical slope, just to remind ourselves. So that's going to be -1. 0 divided by 1 is 0. 0 divided by 0, undefined. So anywhere my y coordinate is 0, we are undefined. Okay. So when I create my little slopes here, anywhere my y coordinate is 0, so where y is 0, where y is 0, okay, we're going to have little vertical pieces. Vertical, vertical, vertical. Where x is equal to 0, we're going to have little horizontal pieces, except 0, 0. And then where my 1, 1, I have a nice pretty 1 slope. Okay, -1, -1, we have a 1 slope. Here we have a -1 and a -1. Okay. All right, so they want us to find that general solution. So we will separate and integrate. I'm going to multiply both sides by y, multiply both sides by dx. I have to show them that I am integrating, so make sure you put your little integral in there. And then y squared divided by 2 equals x squared divided by 2. Remember, we do have a plus c on both sides, but we're going to keep it all nice and pretty on the side with the x. Now, on this situation, they are probably going to multiply by 2, so that's going to give me y squared equals x squared plus c. It's just a constant. We don't have to put the plus c. Sometimes we are, if they ask us to solve for y, we are going to solve for y, but this is actually one of those cases where they probably wouldn't solve it for y in a multiple choice situation, because this is the nice, pretty form of this line or equation. This is a hyperbola. Okay, those are the little guys that either look like this and this, or this and this, but you have your two parabolic shapes. They are not true parabolas though. So they'll ask us to create our little slope field, and right up here is our slope field. This is what they're going to be looking at. Once again, they are not going to be looking at this little T-chart. This is just for us to make sure that we get everything correct, and it's not difficult to make up, and it does help keep you from making errors. All right, and then here's our general solution. General solution. Okay. Now, of course, they're going to have us go backwards. So they give us the differential equation, and we give them the slope field. Now, they're going to give us the slope field. We are going to give them the differential equation. Now, when you're doing this, it's important for you to look at a couple of things. Okay, for instance, when you've got the slope field and you're trying to figure out which differential equation it is, you're going to look at the slope field in the y direction. So you're going to be looking at it, looking up and down. If the slopes change, then that means there has to be a y in the differential equation. So when you looked at this guy right here, notice when you look up and down, the slopes are exactly the same. So that means there's no y in the differential equation. Looking here, as I look up and down, notice the slopes do change, so this one does have a y. This last one, once again, you're looking in the y direction. There is a change in those slopes, so that means you have to have a y in your differential equation. Then you're going to do the same thing in the x direction. So you're going to look left and right. If there are slope changes, then there's an x in the differential equation. So when I look at this first one, notice when I look left to right, the slopes do change, so there is an x in my differential equation. Okay, this guy, as I look from left to right, there's no change, so no x. 4, as I look from left to right, looking in the x direction, there's change, so there better be an x. Okay. Well, when we're looking, once we get to that point where we're looking at this one, you notice you have x's, you have y's, then you need to take it to the next level. And that's where, look where you have vertical segments. Look where you have horizontal segments. Wherever you have vertical segments, look to see which coordinate is on the bottom, because that's where he's going to be 0. Horizontal, you're looking at where that top variable is. So it makes it a little bit nice. You're looking at those vertical segments, looking at those horizontal segments. Let's kind of see what's going on here. Now, I did have to hand make these differential equations because it wasn't on the calculator that was on my computer, and I didn't have time to plug in the program. But you'll get the idea of this guy. So when I'm looking at this, okay, I notice when I look at it from top to bottom, there's a change in y. So the y's change. Remember, delta means change. Okay, as I look at it in the x direction, the x's change. So that means I'm looking for an equation that has x's and y's. So when I look at my answer choices, doggone it, they all have x's and y's. So now I'm going to look for vertical pieces. I have a vertical piece here, so that means I've got to have a fraction. So immediately, without any further ado, I know those guys are gone. Okay, so now I'm going to look at where these verticals happen. Those verticals happen when y is equal to 0. Okay, I'm sorry, yeah, where y is equal to 0. So where my y coordinate is 0, those are done. So that means it's got to be y on the bottom here, so that guy's out of the money here. Okay, so now I'm looking here when x is equal to 0. Okay, when x is equal to 0, ooh, both of those still fit. Darn it. Okay, so we're still duking it out between b and e here. When I'm looking at this, I notice, looking at this, where x is just x to the 1 power, it's not x squared. Okay, so when x is 1, y is 1, that should have a positive slope, and it does. Over here, x is negative, y is positive, that has a negative slope. Ooh, if I had x squared, that negative 1 would be squared, which means that would be a positive slope. That is not a positive slope. So thank you for playing. You're our winner. Okay. So now on this little guy right here, our second one, we look at it from top to bottom. So as I'm looking at it, okay, top to bottom, the slopes don't change. So that means there can't be a y in my differential equation. Okay, the x has changed, so there is an x in my differential equation. Now I'm duking it out between these two. Well, we know that x squared, even if my x coordinate's negative, that's going to be a positive slope. Notice here you have negative slopes, so he doesn't really make sense. So if I'm looking at this one, when x is equal to negative 1, that's where I should equal 0. Sure enough, that's at negative 1. He is our winner. So no matter which way you're going, kind of look back at these. Which differential equation is it? You may have to plug in a couple points and see which one does represent that differential equation. All right, I'll see